we're going to consider techniques of integration that for integrals where it isn't so obvious. There's no general rule about how we need to approach them. So for example, we have the integral of x squared times the square root of 2x plus 1. And this particular function doesn't really fit any general rule that we have. We have a power function, but it's being multiplied by an exponential, and so none of our rules directly apply. But if we could adjust it via substitution so that it would look like something we're more comfortable with, then we could deal with it. So one possibility here, and some of this technique is there's sort of a guess and check. How you go about substituting isn't fixed. But one possibility here is to say I'm going to let u equal 2x plus 1. Setting u equal to that. And if I were to, and so then what that does, if I extend a little bit here, this means that my integral is now x squared times u to the 1/2 dx. And so one issue that needs to be resolved is I'd like to have this all in terms of one variable, and currently I have it in terms of 2. So I need to have a way of solving x squared and understanding that in terms of u, and also dealing with dx. So when we do this, I'm going to take u equals 2x plus 1 and solve that for x. So I'm going to subtract 1 from both sides and divide by 2. And this would mean that x equals 1/2 u minus 1/2. And this also means that x squared is the quantity 1/2 u minus 1/2 squared. And this means from solving for x that the derivative of x is equal to half the derivative of u. And so with a little cleverness, we now have expressions for all of our parts in terms of u. And so we can now rewrite our integral as being the integral. Instead of x squared by substitution, that would be 1/2 u minus 1/2 squared times u to the 1/2, and dx equals 1/2 du, so erase this, times 1/2 du. And now it's just time to clean this up a little bit. So when I clean this up, first I'm going to take the factor 1/2 in front of the integral. And when I expand 1/2 u minus 1/2, I have 1/4 u squared minus 1/2 u plus 1/4. And that is being multiplied by u to the 1/2 du. And from here, if I just distribute in u to the 1/2, I'll have an integral that I can integrate via the power rule. So this would be 1/4 u to the 5/2 minus 1/2 u to the 3/2 plus 1/4 u to the 1/2 du. And now we're able to integrate. So this is 1/2 times, when you integrate 1/4 u to the 5/2, it will go to 7/2. And so this must have been 2/28 minus, this is u to the 5/2, which means this must have been 2/10, and this will go to u to the 3/2, which means this must have been 2/12 plus c. And the last thing that's left for us to do is to return back to the original, get things in terms of x, and I'll multiply in the 1/2. So everywhere there's a u, I know that u equals 2x plus 1. So I'll end up with 1/28 times the quantity 2x plus 1 to the 7/2 minus 1/10 2x plus 1 to the 5/2 plus 1/12 times 2x plus 1 to the 3/2 plus some constant. And again, I can't emphasize enough, there isn't necessarily a way to decide you always do u substitution this way. With some practice, you can recognize which will be most efficient, but we could have easily have chosen to set u equal to x squared to begin with. We just didn't, but we could have done that.